That's still Mr. Ibrahim Aruni. Who is there again? Who is there again? Do you see the screen I'm sharing? If you see the screen I'm sharing, thumbs up. Let me check. Let me double check if you're seeing the screen I'm sharing. Mr. Isaac. Mr. Isaac. Mr. Haruna, I can see you. Okay. We're good to go. In the last class, I took you through different statistical design we have, such as I spoke to analysis of variance, 1-way analysis of variance, 2-way analysis of variance, 3-way analysis of variance, which means that I spoke to one CRD, completely randomized block, completely randomized design. I spoke to randomized complete block design. I spoke to Latin score. I spoke to chi-square. No, I spoke to student t-test, and I spoke to estimation of this analysis of variance package design using real-life data. I remember I delved into differences between 1-way ANOVA, 2-way ANOVA. And I said 2-way ANOVA, 2-way analysis of variance is also called 2-way ANOVA, 2-way analysis of variance is also called 2-way classification of variance, which is also called 1-way elimination of heterogeneity, which is regarded as randomized complete block design. And we have 2-way elimination of heterogeneity, which is regarded as Latin square. And I told you assumptions of Latin square. I told assumptions of RCBD and assumptions of CRD. I further delved into assumptions of basic principles of Latin square. I spoke to hypotheses. I took you through hypothesis. How you it remains hypothesis until it is verified. It remains hypothesis until it is verified. So how we can draft null hypotheses, how we can draft alternate hypotheses, I took you through all that. We use the real life data to estimate analysis of variance. We constructed variance with another table where we calculated sum of square, we calculated total sum of square, we calculated correction factor, where I told you correction factor is also called adjusted term. Then we spoke, and I took you through how to calculate sum of square. We calculated mean square, we calculated F ratio, and I took you to the decision rule, which will guide you in taking conclusion. Am I speaking sense? Am I speaking sense? Am I speaking sense? Am I speaking sense? If you are speaking sense, thumbs up, let me see you. I'm still Mr. Ibrahim. I'm still Mr. Ibrahim. I told you in the last class what makes an experimental design what conditions before you use a particular design for your experiment. Now, I took you to student T-test. When I say student T-test, I took you to post-op test, where for determining level of significance, that is the mean separation tool, which helps us to determine level of significance. We found through our analysis of variance that where FCAL is significant. And I said we will not always stop there. We need to go further to discriminate between these means. We've established that the means, we've established that our F calculated is significant. Now, we should go further to discriminate between the means. Discriminate between the means in the sense that to differentiate them into level of significance, which will help us to know which mean is more significant than others, which will help us to make a judgment, to make a reference judgment in our conclusion. Am I speaking sense? Am I speaking sense? Am I speaking sense? Just give me a thumbs up. I see Mr. Aruna. I'm seeing Mr. Aruna. I'm seeing Caesar. Caesar, you are Mr. Caesar, you are welcome. I see Mr. Caesar. I see Mr. Talca, Mr. Isaac. Okay. Now today, we'll be speaking to chi-square. Chi-square, which is a test of goodness of fit. You know, when you are doing a molecular analysis or genomic analysis, you are studying genetic structure, gene structure in a population. If you are doing a population base, if you are doing a population-based study in terms of genetic structure, you want to know in a population how, for instance, let me say, I am screening Nigerian population of Zebo cattle, White Fulani, Chokoto Gudali, Ambala, and Red Bororo. I'm screening them for their thermotolerant potential at HSP70 gene locus. At HSP70 gene locus, I want to screen Nigerian cattle for their thermotolerant potential. For me to do this, I need to take blood sample. I will do DNA extraction. I will do PCR. I will do sequencing. Then I will further do bioinformatic analysis to identify, to detect SMP locus or SMP variant within that population. So the SMP variant I will identify, I can go further to construct SMP genotypes, which will be associated to thermotolerance trait. Then I would know maybe SMP genotype at so locus lowers body temperature, or it does not lower body temperature. Now, for the fact that a gene is present in a population does not mean that gene is doing a significant work in that population. A gene may be present in the population and that gene may not be doing anything. For instance, from the work I have done, I have found SMP genotype at HSP70. And I screen Nigerian cattle for HSP70 gene. And I associate the SMP genotype detected to thermotolerant. The striking finding there is that though all of them are they have inherent DNA, all of them, the population have HSP70 inherent in the DNA. But it's only heterozygous SMP genotypes that are lowering temperature. Homozygous SMP genotypes is not lowering temperature. But heterozygous form of that gene is one that succeeds in lowering temperature. What our Zebo cattle in Nigeria, for instance, exhibit thermotolerant potential because they have heterozygous form of HSP70 in their gene, in their genome, or in their DNA sequence. Am I speaking sense? Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. Now, this is where I'm going to. For the fact that a gene is present in the population, whether in heterozygous form or in homozygous form, we cannot just quickly rely on that gene and make judgment that the gene is not responsible for this variation we are seeing. We must subject it to Hadamard equilibrium. And you get what I'm going to now. We must subject that gene, though we have found that the gene is having significant influence in the population. For instance, a heterozygous form of SMP genotype of HSP70 is having significant influence on lowering temperature, on lowering heat stress, on lowering temperature, on lowering heat stress, conferring thermotolerance potential on our cattle. Now we must subject the genetic structure, the gene in a population to Hadamard equilibrium. And for us to do that Hadamard equilibrium, the tool we use is chi-square. It is chi-square we used to know. We can only rely on that gene that truly it is this gene that is lowering body temperature in the population of Nigerian cattle. Then we subject to Hadamard equilibrium. And Hadamard equilibrium says gene will remain constant. It's like network is back. Okay, network is back. Fantastic. Network is back. Fantastic. Now, what I was saying, we have found that SMP genotype of HSP70 lowers body temperature in Nigerian cattle. Nigerian cattle are able to exhibit homogeneous potential because of the presence of heterozygous form of SMP of HSP70. But we'll not quickly jump to conclude. We subject the genetic structure at that locus to adiabatic equilibrium, and which tells us in population genetics, which tells us that gene remain at equilibrium. Gene frequency remain constant. They remain at equilibrium when they're not being affected by migration, when they're not being affected by bottlenecks, like founder's effect, like associative mating, like inbreeding. When all those things are not there, the gene will remain at equilibrium, meaning that the gene will not tend to towards fixation. Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. So the reason we are subjecting our genetic structure to adiabatic equilibrium to know that actually it is the gene that we detected is responsible for variation in the population. If there is associative mating in that population, or there is inbreeding in that population, inbreeding tends to drive the population towards fixation, towards homozygosity. Maybe the population has even been fixated for a particular gene, meaning that it has reached 100% homozygosity, meaning that the entire population is now fixed for one gene. Obviously, that population will behave in the same way. So if you use that information to make judgment, it is not true, because what we are seeing, this population is a result of inbreeding, or it's a result of founder's effect, or it's a result of bottleneck. Maybe bottleneck. Maybe we have heard of a genetic drift, meaning that maybe the small population that is disaster. When disaster happens, the number of population reduces, and they have to migrate to another area to establish their life. So we have found that effect, small number of individuals that will go and establish. Then inbreeding will be high in such population. Inbreeding will be high in such population. Those ones are called genetic drift or bottlenecks. So we will test a genetic structure, whether they're in equilibrium. So if they're in equilibrium, then we know, if they're in adiabatic equilibrium, then we know that what we found in this population is actually the effect of the gene. Am I speaking sense? Am I speaking sense? Now, how do we subject our genetic structure to adiabatic equilibrium? We do that with the aid of chi-square. In Christ, so we want to study the goodness of it. Meaning that this population is behaving as a result of no influence. No influence. It's in equilibrium. There's no founder's effect, there's no migration, there is no associative mating, there is no genetic drift. It is equilibrium. That is the exact nature of this population anywhere. So if anything now comes that trigger it off equilibrium, then we begin to observe. That is null hypothesis. Like I told you that in the last class, null hypothesis are presence of no effect, of zero effect, while alternative hypotheses are presence of significant effect. Now, so the set of goodness of it, the animal is fit. No issue. Anything can happen that or is not fit. Am I speaking sense? Am I speaking sense? Network is just behaving about I'm back. Am I speaking sense? Oh my goodness. Okay. Network is bad today. Network is really, really bad today. It's really, really bad today. Network is bad. Okay, still network is coming back. If you are there, thumbs up, let me see you. If you are there, thumbs up, let me see you. Okay? I can see Mr. Musa. I can see Mr. Yusuf. It's okay. It's okay. So that is why we have to do subject and the structure from the equilibrium, so that we're able to tell if it's the gene in that population that is causing the variation we are seeing. And we do that through chi-square, which is the final test of goodness of fit. Which is the test of goodness of fit. Okay. Are we good to go? Fantastic. Now we now want to delve into real life application of chi-square. Am I speaking sense? Am I speaking sense? No, I'm not speaking sense. Okay. Now, I have explained to you what chi-square is. And how do we apply chi-square? How do we apply chi-square? How do you apply chi-square? Let me share my screen. Let me share my screen with you. Let me share my screen with you. Then you see what I want to do. Are we good to do that? Now, what I'm saying is this. What I'm saying is this. We need chi-square to test whether the data is fit, meaning that nothing happens to the data. If there is discrepancy, it's just a discrepancy. That's what chi-square does. If there is discrepancies, it will tell us. If there's no discrepancy, it will tell us. If the data is fit, it will tell us. If it's not fit, it will tell us. If a dependent variable, if an hypothesis is of zero effect, it will tell us. If it's of zero effect, it will tell us. If it's of zero effect, it is fit. Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. Now, when you, for instance, let us take the data as an example. Let's take that as an example. An animal breeder raised 100 piglets for color, for body color, from a cross that is hypothesized to be ratio 3:1. From the cross that is hypothesized to be ratio 3:1. That is, in this crossing, we are expecting to observe ratio 3:1 of phenotypic ratio of 84 black, 84 white, 16 black. Am I speaking sense? Am I speaking sense? Fantastic. So although out of this 100 piglet swine, out of this 100 piglet, the swine breeder was expected to produce a phenotypic ratio of 75 white, 25 black. That is expected. You know, the chi-square talks about observed and expected. If there's no difference, let me make this clear. If there's no difference between the observed and expected, we say we establish goodness of it. Get that? If there's no difference between the observed and if there's no discrepancy between the observed and the expected, we establish goodness of it. Meaning that the population is in equilibrium. Nothing is changing it. Nothing is causing it off balance. Am I speaking sense? Am I speaking sense? So, chi-square is a test of detection of discrepancy. And how do you know the p-value of chi-square? Ordinarily, the p-value is p less than 0.05 is significant, isn't it? When p becomes not significant, when p is greater than 0.05, it's not significant. And if we have 5% level of significance, meaning that what we are seeing in the population is a result of 5% per chance and 95% as a result of our independent variable. I have explained that before. Now, if our p value is insignificant in chi-square, if the p value is insignificant, then we establish goodness of it. Then there's no difference between the observed and the expected. That is why the p-value is not significant. Am I speaking sense? Am I speaking sense? Am I speaking sense? Because there's no significant difference between the observed and expected, then our p-value will be insignificant. But if something comes into that population, cause our population off balance, and p-value becomes significant, then our population is no longer in equilibrium. For our population to be in equilibrium, p-value must be insignificant. So when you run your chi-square, you are taking a look at genetic structure. For instance, SMP genotype, those ones that are not significant, that is the one that you will pick, that are really reflecting the population, because the agent of population evolution, has not disrupted the population. When the agent of evolution has not disrupted or agent of population have not disrupted the population, then the population is equilibrium. You have no genetic drift, you have no inbreeding, you have no associative mating, you have no standard effect, you have no bottleneck. The population is in equilibrium. Agent of evolution has not disrupted it. But when agent of evolution disrupted your population, it will toss it off the balance. It will be all out of Adewenberg equilibrium. This is what Adewenberg told us, or postulated, or found. So, for you to establish goodness of fit, there is no discrepancy between observed and expected. The p-value will not be significant. When the p-value is not significant, then there are two differences between the observed and expected. We may say, how do you construct null hypothesis in chi-square? Null hypothesis can be constructed. There is no difference between observed and expected. That is null hypothesis. And say that the discrepancy between observed and expected, that is null hypothesis. That is alternative hypothesis. If there is no discrepancy between observed and expected, then we have effect of our null hypothesis is of zero effect, is of no effect. Am I speaking sense? Because there's no discrepancy between observed and expected. Now, but let me come again. What I mean is, null hypothesis, chi-square takes goodness of fit. It tells us, it establishes where there is discrepancy between the observed and expected. Expected is how the population is supposed to be. Our population is supposed to be in equilibrium. No mutation, no migration, no founders effect, no associative mating, no inbreeding. Our population is in equilibrium. Homozygous dominant, heterozygous, homozygous recessive, they are at equilibrium. That's the balanced population in nature. Am I speaking sense? Am I speaking sense? Am I speaking sense? That is expected. That is expected. Now, the observed can be maybe mutation comes into the population, migration happens, standard effect happen, bottlenecks happen. It has touched our population out of the Adewenberg equilibrium. Now we begin to study extent of variation that happens. So when we eventually observe that this population is no longer in equilibrium, meaning that the observed is no longer correlating with the expected, that means that the population is no longer in equilibrium. Am I speaking sense now? Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. So now, statistically, how do we now know if our population is not in equilibrium? Meaning that the observed is not the same with expected. So the null hypothesis in chi-square summarily tells us that observed is not the same with observed is the same with expected. There's no difference between observed and expected. That's null hypothesis. I mean, like nothing is changing. The population is in equilibrium. Nothing has changed it. If the down alternate hypothesis will now be that a discrepancy between observed and expected, meaning that something has entered this population and it has taught the population out of Weinberg equilibrium. Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. Fantastic. Now, the p-value here is when does p-value here will be p less than, when we have p less than 0.05. When p is less than 0.05. When p is significant, meaning that something has entered that population and it has forced it out of equilibrium and it is causing a significant variation. That's when p is significant. Then something has entered that is discrepancy. When p is not significant, when it's not significant, that tells us that in that population, nothing is changing, because the founder's effect, evolutionary factors, is not changing the population. Everything is at chance. Am I speaking sense? Am I speaking sense? Am I speaking sense? Am I speaking sense? Let me come over again. You know, p-value, our p-value in ANOVA and other is somewhat different when we are using at the Weinberg equilibrium. When we're using at the Weinberg equilibrium, normally p-value, p less than 0.05, meaning that we have 5% of 5% probability, meaning that what we saw in our experiment is 5% due to chance and 95% due to our independent variable. Am I speaking sense? That is the mean of 5%. That is the mean of 5%. If at 1%, thank you. So if our level of significance is 1, you know, I told you yesterday, I said when we are checking level of significance, we can check at 5%, FCAL. From the, we can check at 5%, we can check at 1% level of significance. So if it is 1%, meaning that there is what happened in our experiment is 1% due to chance and 99% due to our independent variable. This is statistical interpretation of 5% level of significance, 1% level of significance. Am I speaking sense? Am I speaking sense? Am I speaking sense? I'm seeing Mr. Caesar. Fine. Now, in chi-square, there's a big difference. Like I told you, if we are using chi-square to estimate whether there is whether our population is at the Weinberg equilibrium or is it not in at the Weinberg equilibrium, we use chi-square to establish whether a population is at the Weinberg equilibrium or it's not at the Weinberg equilibrium. If our population is in and the hypothesis to test in that situation is there is no discrepancy between the observed and the expected. That is null hypothesis. An alternate hypothesis will be that a discrepancy between the observed and the expected. At the Weinberg equilibrium is the observed, is the expected. Sorry. At the Weinberg equilibrium is the expected. Is the expected. So if evolutionary factors come into our population, it will toss it off at the Weinberg equilibrium. Then the observed will not be different from the expected. That is alternate hypothesis. Am I speaking sense? Am I speaking sense? Fantastic. So that is how you can use chi-square. That's how we use chi-square to study Wimberg equilibrium in our population. Am I speaking sense? Am I speaking sense? Another thing we do, another area where we apply, I just want you to have a concept, understanding of how we use chi-square. How we use chi-square. Now, when you use chi-square is to test discrepancy. I'll give you a live scenario when you are testing genetic structure. Is our genetic population structure, is it in an equilibrium? For you to know that you use chi-square to do that. So if we are trying to tell whether our population structure is in equilibrium, genetic structure is in equilibrium. And what then by genetic structure? We carry out blood, a PCR, we study gene, for instance, SMP. We study single nucleotide polymorphism SMP variant at HSP70 in our population. We establish the SMP variant, we establish the SMP genotype. These are genetic structure. We found the gene that is lowering temperature. But before we conclude that this is the gene that is doing it, we must object it to Wimberg equilibrium. By doing that, we submit to chi-square analysis to determine whether it is at the Wimberg equilibrium or it is not. If it's at the Wimberg equilibrium, then the gene we found, or the genotype, SMP genotype we found, is responsible for lowering of temperature in our population. Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. Another way where we apply chi-square, if you're just looking for differences between observed and expected. For instance, in this example, an animal breeder raised 100 piglets for body color from a cross that is hypothesized to result in ratio 3:1. Remember, in simple Mendelian inheritance, monohybrid crossing give us phenotypic ratio of 3:1. Monohybrid crossing. And a genetic phenotypic ratio of 84 white and 16 black were observed. That is observed. Although out of this total 100 piglet, the swine breeder was expected to produce phenotypic ratio of 75 white, 25 black. That is expected. That is expected. You see the expected here now, and you see the observed. Am I speaking sense? Am I speaking sense? We want to know, can we establish goodness of fit? Is our observed the same thing with expected? When the observed and the expected is the same, then there is goodness of fit between them. Am I speaking sense? Am I speaking sense? Fantastic. Fantastic. Now, like breeder, that if you do monohybrid crossing, you're supposed to see, in terms of color, in pig, we're supposed to see 84 out of 100, 84 white piglet, 16 black piglet. That is what we see. But what we're expected to see is 75 white, 25 black. And we saw 84 white, 16 black. That's what we observed. Now, let us establish if there is goodness of fit. We can't just say because there are differences in the number, it is not fit. We need to use chi-square. So these are the areas why we use chi-square in analysis. So when you are doing research and your research is in tandem with a kind of concept, then you use chi-square to establish discrepancy between observed and expected. Am I speaking sense? Am I speaking sense? Fantastic. Fantastic. Now, the question is, hypothesis to test is whether the observed frequency, which is 83 white to 16 black piglet, deviate significantly from the expected frequency, which is 75 white, 25 white, 25 black. 75 white, 25 black. The question is, construct both null and alternate hypotheses for the experiment above. Or construct null hypothesis. Null hypothesis and alternate hypothesis for the experiment above. Question 2 says, state the decision rule from here above. 3 says, calculate chi-square. And 4 says, you conclude. Let's go. Isn't it interesting? Isn't it interesting? Isn't it interesting? Our understanding of this basic statistical design will let us know where to apply them in our experiment. Am I speaking sense? Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic, fantastic. Now, our decision rule is this. Are you seeing this? If you are seeing this slide I'm sharing, thumbs up. If you are seeing the slide I'm sharing, thumbs up. Fantastic, fantastic. Now, the alternate hypothesis is the frequency of phenotypic ratio observed, 84 white to 16 black piglet from the experiment do not significantly deviate from the expected phenotypic frequency ratio of 75 white, 25 black in 3:1 phenotypic ratio. While alternate hypothesis will now say the frequency or phenotypic ratio observed, which is 84 white to 16 black piglet from this experiment significantly deviated from expected frequency of 75 white to 25 black piglet in ratio 3:1 phenotypic ratio. The decision rule is this. And like I told you in last class, the decision rule is the same, but for both ANOVA, for both t-test, for both chi-square, the decision rule is the same. Even t-test is the same. If S calculated is less than S tabulated, you'll accept null hypothesis by rejecting alternate hypothesis. On the other hand, if S calculated is greater than X tabulated, you'll accept alternate hypothesis and reject null hypothesis. You realize that the decision rule is the same. The concept of decision rule is the same. Let's move forward. Now, how do we calculate chi-square value? How do we calculate a chi-square value? We perform a chi-square value I'm coming. You know, in simple chi-square, we use the formula for chi-square is observed frequency minus expected frequency raised to power 2 over expected frequency. But network is misbehaving here. Let me get it right. I'll be able to share it with you, share the screen with you. It's okay. It's coming up. It's coming up. Fantastic. No. Okay. It's coming up. It's coming up. Okay. Oh my goodness. Okay. Oh, no. I'm coming. Okay, I'm almost there. Now, I've spoken to decision rule. Now to calculate our S square. So see, you can see from the slide I'm sharing, S square is summation of observed frequency minus expected frequency raised to power 2 over expected frequency. OF minus EF square raised to, in bracket, raised to power 2 over EF. OF is observed frequency, EF is expected frequency. And we have degree of freedom, DF, K minus 1. K minus 1. And we are doing between black and white. Black and white. That's the frequency, black and white. Now look at the table. There we go. This is the table. We have 84 white. We have 16 black. Observe frequency. Observe what? Frequency. Am I speaking sense? Am I speaking sense? Now, we are the data generated, the data provided in the table, in the question is summarized here. We have white observed frequency. We have observed frequency 84 white. Expect observed frequency is 16 for black. We have expected frequency 75 and for white, and expected frequency 25 for black. Now let us calculate. What we have observed and expected. Now we have to calculate chi-square. Look at the chi-square formula. I said observed frequency minus expected frequency raised to power 2 over expected frequency. Isn't it? Isn't it? Now, so we now said we calculate 1 for black and white. Let us say 84. Let us do 84 for 80. Let us do for white first. For white first. 84, which is observe minus over we have now we will do them for black, we will do for white, and we will add it together. We will do for black, we will do for white, we will add it together. See, so that is if it is more than, if the variables are more than 3, we will be doing it for white, for black, for yellow. That's how you will do it. Now, look at the white. Observe is 84. Observe is 84 minus expected 75 raised to, in parentheses, raised to power 2 over 25 over 75. We go to black plus, which is black, observe 16 minus expected 25 in raised to power 2 then over 25. When we do that, then we add the two together, we get our chi-square value. Will be 4.320. Am I speaking sense? Am I speaking sense? Am I speaking sense? Am I speaking? Fantastic. 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 So we have got the chi-square value for the two variables, black and white. We'll go further. Haven't done that. We need a chi-square value. We need a chi-square table, like the one I taught you yesterday in the last class. That the tabulated, we use tabulated and calculated. And don't forget, from our decision rule, we have got our expected of calculated to be 4.320 at 1 degree level of significance. When we check the chi-square table, we will get 3.841. That will be extrapolated from the table. Do you have the table with you? You have the table. But are you familiar with chi-square table? Are you familiar with the chi-square table? Well, fantastic. Fantastic. But I will do more clarification when we have physical class. And do that physical class, we still do revision, and I'll put you through how to check this information on maybe F table, T table, chi-square table. Am I speaking sense? Am I speaking sense? Now, if you check the degree of freedom on chi-square, so, and we check the degree of freedom here, it is 2. Let us see K. Let me show you. The degree of freedom is K minus 1, which is 1. So on the vertical side, you will see the degree of freedom on the table. So when you check it correspondingly, on the table, you will have 8 points. You will have 8. You see, can you see it? This is what you obtain from the table. So what you obtain from the table is X tabulated, and which is 3.841. And our S calculated is 4.320. You can see from the division rule, we now conclude, since S calculated 4.320 is greater than X tabulated, we therefore accept null hypothesis, which says, because you have to tell us that what null hypothesis says, which says frequency or phenotypic ratio observed, meaning that 84 white and to 16 black from the experiment significantly deviated from the expected phenotypic ratio, which is 74 white, 25 black, in 3:1 phenotypic ratio at 5% level of significance. We conclude, therefore, that phenotypic ratio observed from across, from the crosses of white and black coated pig deviated significantly from the expected phenotypic ratio. Then there's no way of observed that there's no goodness of it. That is different between the observed and expected. Am I speaking sense? Am I speaking sense? Isn't it simple? Isn't it interesting? Now we can have understanding of statistical understanding of how we can apply this statistical design to solving our experimental problems or the data generated from my experiment. I want to go further to teach what's called chi-square using contingency table. Using contingency table, I want to show you possible scenarios where you can use chi-square to perform statistical analysis. We are moving forward to chi-square using contingency table. In this scenario, we'll be speaking to, for instance, we have male and female. A population of human beings consists of male and female, and there is COVID-19 outbreak. How do male and female respond to COVID-19 outbreak? Do they demonstrate susceptibility or they demonstrate resistance? That's an analogy of, in that, if you seek a kind of research concept like that, then this is a kind of statistical tool you can use to analyze it and explain it. Let us take a look at this question. Are we good to go? Fantastic. Consider a population of 150 pigs challenged with swine fever disease. The following data represent the number of males and females resistant and susceptible to swine fever disease. Hypothesis to test is hypothesis to test is that resistance or susceptibility is independent of sex. meaning that maybe it may be genetic. So we want to know resistance to infection or susceptibility is independent of sex, and we are giving this data. The question is, state the null hypothesis and alternate hypothesis, state decision rule, and calculate chi-square value and draw reference conclusion. How do we do this? The null hypothesis. The null hypothesis is resistance, and so now here is we are taking discrepancy. Discrepancy in both male and female supposed to respond the same way. There should not be difference in the response of the male and female piglet to swine fever outbreak. There should not be, for no reason, there shouldn't be differences, no discrepancy in their response. That is null hypothesis. Am I speaking sense? Am I speaking sense? Now, we want to see if there is discrepancy. So null hypothesis is resistance and susceptibility is independent of sex. So sex does not have effect. That's null hypothesis. Sex, somebody may even say sex does not affect resistance and susceptibility of pigs in response to swine disease outbreak. Some may say there's no difference in both resistance and susceptibility, or sex does not affect resistance and susceptibility. Alternative will say sex affects resistance and susceptibility of pig to swine disease outbreak. So somebody may use another language, say resistance and susceptibility is independent of sex, while alternative to be resistance and susceptibility is dependent of sex. Am I speaking sense? Am I speaking sense? Am I speaking sense? Isn't it interesting? Fantastic, fantastic. The decision rule is the same. X calculated is less than X tabulated, accept null hypothesis. X calculated is greater than X tabulated, accept alternate hypothesis. Accept alternate hypothesis by rejecting null hypothesis. Accept alternate hypothesis by rejecting null hypothesis. Am I speaking sense? Am I speaking sense? You accept, but in here you accept alternate hypothesis by rejecting alternate hypothesis. Am I speaking sense? Am I speaking sense? Fantastic. Fantastic. I'm coming. I want to make something very clear here for you so that you get it very clearly. Fantastic. Now, we have to calculate expected frequency. In contingency table, there is a slight difference in how we calculate expected frequency. In contingency table, if you want to calculate the expected frequency, all you will do is, can you see, you say R subscript I C subscript J over N. Overhead, meaning that the total in row times the total in column overhead. That's what it means. Where R1 is total frequency in row, while in row I, and Cj is total frequency in row J, and N is the total number of sample. Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. We're good to go. Now, having known that, let us do the calculation. The first thing is we calculate expected frequency for susceptibility for male and female. We calculated expected frequency for resistance, male and female. We generate the table. Am I speaking sense? Am I speaking sense? Am I speaking sense? Fantastic. Fantastic. Now, how do we do it? Look at this. Expected frequency for susceptible, male and female. So what do you do here? Remember, we say expected frequency is RICJ over N. So we pick here. We are talking about for susceptible for male. So total enrolled for male is 63. Total enrolled for male is 63 times total in column for male is 85, is 65. Susceptible. We are talking about susceptible. Total enrolled. Am I speaking sense? Am I speaking sense? Are you following? Fantastic. So, total enrolled. Total enrolled for male is 63. Total in column for susceptible. Because we're talking about susceptible is 65. Then 63 times 85, 63 times 65 over 150. What is E50? Expected EF. That is N, total number of observation, N, 150. Now be 63 times 65 over 150, we get 27.3 for male. We calculate for female. Total enroll for female is 87. For total enroll for female for susceptible, total enroll for female, for total enroll for female is 87. And total enroll for susceptible is 65. So it's 85 times 65 over 150. We get 37.7 for female. So we have calculated expected. You know, they gave us observed from the experiment, which is given in the table. Now we have calculated expected for susceptible, male and female. Then we'll go to calculate for resistance. Total enroll for male. Let me put it very clearly. 63, then put male. Male. Let me put female so that you're going to get it very clearly. Am I speaking sense? Am I speaking sense? Fantastic. Mr. Okwamza, you are welcome. Now, expected frequency for resistance. The total enrolled for male is 63. Total enrolled for male for resistance is 85 over N total observation. We get 35.7 for male. We do the same thing for female. Total enrolled for female is 87. Total enrolled for female is 87. And the total enrolled for resistance is 85. So 87 times 85 over 150, which is N, we got 49.3 for female. Then we have succeeded in calculating our expected frequency. Let us key this into the table. You see here now, we have resistant expected, resistant, susceptible. This is our expected. So for expected for male, you see resistance there. Now, we will now use this one. We'll go further to calculate the chi-square. Because we did expected and observe to calculate the chi-square. Now, we calculate the chi-square for resistance. Calculate the chi-square for susceptible. We add them together. Then we get our chi-square value. Now, let us calculate chi-square for resistance. You see, and the formula is observed frequency minus expected frequency raised to power 2 over expected frequency. Isn't it? Isn't it? Isn't it? That is formula for chi-square. Isn't it fantastic? Now, our observed here is 35. Expected is 35.7. Then 35 minus 35.7 raised to power 2 over expected frequency 35.7. We'll get 0.014. We'll come for male. Female will do the same. Expected 50 minus observed 50 minus expected 47.9 raised to power 2 square. Coming. Correct. Square over 49.3, we get 0.010. Am I speaking sense? Am I speaking sense? Fantastic, fantastic, fantastic. Now, so for the total chi-square value is equal to x squared, chi-square. Chi-square. We have got chi-square value for resistance. Am I speaking sense? Can you see? Can you see? For resistance. Fantastic. Let us go to chi-square for susceptible. Susceptible. For susceptible. Here we have expected. Expected. We have 28 minus 27.3 raised to power 2 over 27.3. That is expected. Then we'll have 0.018. We do the same. 37 over 37 minus 37.7 raised to power 2 over 37.7. We get 0.013. Then expected. So the chi-square value for susceptible is 0.031. Then we add these two together. Summation of resistance. Summation of resistance. Resistance and susceptible chi-square values. And susceptible. Susceptible chi-square values. Am I speaking sense? Am I speaking sense? Then when we add the two together, we get 0.05. The 0.05 is our S calculated. 0.05 is our S calculated. 0.05 is our S calculated, which is our S what? X calculated. S calculated. Now, we say there we proceed. Look at it here. Degree of freedom, which is now we have got our K minus 1. Degree of freedom here is this. Rho minus 1 in parentheses times column minus 1. That is how we determine a degree of freedom. Then 2 minus 1 times 2 minus 1, we get 1. Alpha means at 0.0 level of significance. 0.0 level of significance. 0.0%, 0.0 level of significance. That is p-value. That is alpha. So S squared, when you say alpha, it means level of significance, 0.05%. 0.05, which is 5%, 0.05. It's got to F calculated. So S cal at 0.05 level of significance at 1 degree at 1 degree of freedom is equal to 0.005. Then we look at our S tabulated. S squared at alpha level of significance, degree of freedom is equal to S tab. And when we check the table, we will get our S tab to be 3 the way it was, or the way it was in the previous scenario will estimated what we performed. So S tab at 0.05 at 1% level of at 1 degree of freedom will give us 3.841. Am I speaking sense? Am I speaking sense? Our decision rule is there. S cal, if F cal is less than S tabulated, will accept null hypothesis. But if S cal is greater than X tab, we do what? We accept alternate hypothesis by rejecting null hypothesis. We accept alternate hypothesis. Am I speaking sense? Am I speaking? If I'm speaking sense, thumbs up. If I'm speaking nonsense, thumbs down. Let me check if you are following what I'm saying. Fantastic, fantastic, fantastic. Now we conclude. Since S calculated 0.0055 is less than S tabulated 3.841, we therefore accept null hypothesis, which says resistance and susceptibility is not significantly affected by sex. That's all. Isn't it interesting? Isn't it interesting? Isn't it interesting? Fantastic. So I've been able to, at the end of this class, I've been able to let you understand different statistical packages we have in animal science or life sciences, and the understanding of each statistical package, assumptions behind them, principles behind them, and where they can be. When you perform your experiment, you'll be doing your project. The data you collect, you experimental. Then when you are writing your proposal, get am I speaking sense? Am I speaking sense? And you'll have a better understanding in terms of interpretation, in terms of discussion, because you know where to use ANOVA, where to use one way, where to use two way, where to use Latin square. you know where to use chi-square. If it is chi-square, if it is contingency table, you know where to use contingency table, where to use t-test. Doing all of this, I have come to the end of this class, and I've come to the end of my own first section. Your curriculum does not involve student t-test and chi-square, but I felt this part of a statistical package will be useful when you encounter data that you need to use chi-square. You will be able to choose as appropriate the statistical design or package you will use. At the end of this class, I know you have been equipped. You have been equipped in terms of the understanding of statistical design we have and how and where to use them. I thank you for giving me your time. Thank you for giving me your time. We still have a physical class to do revision and interact. And for those that will be doing genetic engineering, same time tomorrow, we're going to start genetic engineering. So, Mr. Isaac, please, the HOC of animal breeding option should call me. Get the HOC of animal breeding option, get a call, put a call across to me. At the end of this class, I'm going to merge the summary of this class. I will merge them together. I'll forward it to you. The video version, I'll forward it to you. But the last class, I couldn't record the last class. I didn't know what happened. I prompted auto record, but it didn't record. But I'm recording this. I'm going to forward this to you. And I can tell you, if you read the summary that I'll be forwarding to you, you are good to go. 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 So thank you very much, and God bless you. It did not even record. It did not record. It did not record. It did not record. As it's coming on and on, it didn't record. You stop recording. You record. So I will just send the. So, recording. Let me just what is doing. We don't record. 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 The fluctuation of the fluctuation, yes. The fluctuation.